There we go. And they're all a little bit review and a little bit new, okay? So prior to today, we had been looking at elements and compounds, and now we're going to look at a mixture, the difference between a mixture and a compound. A compound is not a mixture. A compound is actually a pure substance. And this is page 49. And how we know it's a pure substance, in a pure substance, all the particles are the same. So if we have a pure substance, all the particles are the same as each other. So both of these samples of matter, the sample on the left and the sample on the right, contain hydrogen and oxygen. But over on the left, we have O2 particles, and we have H2 particles. So in other words, we have different particles. And if the particles are different, we do not have a pure substance, we have a mixture. So if the particles are different, we have a mixture. So different particles mean that it is a mixture. The H's are not bonded to the O's. So we have two separate elements, not a compound. On the other hand, over on the right, all the particles, are they the same as each other or are they different to each other? Yeah, they all look like little Mickey Mouses, yes? Okay, so all the particles are the same. Okay, they all look like a little Mickey Mouse. And what does that tell you? If all the particles are the same, you must have a, not a mixture, but could be a compound, but it could also be an element. If all the particles are the same, you know you have a pure substance. In this particular case, we have H is bonded to the O. So we have two different elements. And they are bonded together, and that makes it a compound. But all the particles are the same, so it's a pure substance. So compounds are pure substances. All compounds are pure substances. As long as you don't mix it with another compound, because if you mix it with a different compound, then of course you have a mixture because you have mixed it. But we'll take a look at that a little bit later. Okay. So any compound on its own is a pure substance because all the particles will be identical. Now, comparing elements and compounds and mixtures and compounds, it is safe to put sodium chloride on your fish and chips, okay? Just gives it a nice little punch of flavor, but it would not be safe to use sodium and chlorine. So NaCl, which is a compound, is okay, tasty. Sodium, which is a metal and is a solid, and Cl2, which is a gas. These are together two elements. Explosive, toxic and explosive. That's a little S. That tells you it's a solid. And after the Cl2 is a gas, a little G, it tells you it's a gas. Toxic and explosive. NaCl is non-reactive and tasty. And we're going to take a quick look at a little video. We don't do this in the classroom because chlorine gas, as I said, it is toxic, and toxic gases are really bad because, of course, gases will move everywhere, and you certainly don't want to be inhaling chlorine gas. That was one of the chemical weapons used in World War II was chlorine gas. Okay, it sort of melts your lungs, which is not so good. All right, so we're going to go now to a short video clip from Mr. Nile Red. I don't know if that's actually his name, but that's his channel. Okay, and we'll turn on the volume here. And we will watch him deal with toxic chemicals so that we don't have to.
Up to make some table salt, also known as sodium chloride. So just from the name sodium chloride, you can pretty easily see that it has two major components, sodium and chlorine. On their own, both elements, sodium and chlorine, are pretty reactive and dangerous. However, interestingly enough, when they are combined, they form a nice edible salt. This is an interesting demonstration that shows how drastically different the properties of a compound can be compared to its components. So for the first step, I'll cut off a small piece of sodium that I'm going to be using for the reaction. Sodium metal is actually quite shiny, but it quickly reacts with air and moisture and forms a white coating. You can see.
Can you see the shininess in there after it's been cut? Because it is shiny, that will be one clue that will tell you it is a certain type of element. What types of elements are shiny? Metals, okay? So metals are shiny. So sodium is a metal. And in fact, if you look over on the leftmost column of the periodic table, it is the third element down, Na. You can look over here or over here. But if you look on that one, you can see it's in the blue section, which means those are your metals. And the first column are called the alkali metals. Does that sound familiar? Okay, we'll learn more about that later. But alkali metals are so soft, you literally can cut them with a knife or a scalpel. And we'll actually do a little demonstration in the periodic table section so you can see that. Okay, so here we go. That is our sodium metal, shiny.
See a bit of the shininess after it's cut on the bigger piece. The liquid that you see dripping off the sodium is mineral oil, which is what the sodium is stored in.
They store it in mineral oil so that the oxygen from the atmosphere doesn't get added as much, and also to keep any moisture away because sodium is violently reactive with water.
This is my chlorine generator. Inside the flask is chlorine pool pellets. I then poured hydrochloric acid into the flask and it reacts to produce chlorine gas.
What color is the chlorine gas? Kind of a yellowy, greeny kind of color, yes? Okay, that is the color of death. If you breathe that, you will not be happy.
As you can see, the chlorine has a faint greenish yellow color. The top is blocked, so the chlorine is forced down the hose. The hose leads into a larger flask with sand at the bottom. The sand is at the bottom to prevent the glass from cracking from high heat. Inside the flask is then dropped a small pellet of sodium. This is half of the piece that I cut off in the earlier shot. A little water was added to get the reaction started, but I think I added a bit too much. The white cloudiness that you see is a suspension of really small particles of sodium chloride.
So even though sodium chloride is at room temperature a solid, because it has just been created in this explosion, it's kind of those solid particles are right now suspended in the air. So the reason it looks cloudy is because you're seeing solid particles suspended. Yes? Yep. Right? Crazy. I know. Yes, you could eat it when you're done. So let's take a look at what you could eat. It will become more apparent in just a moment.
The white stuff on the walls is also sodium chloride. When a lot of the sodium chloride cloud has dissipated, it's a lot easier to see a lot of the white sodium chloride all around the flask.
Okay, so you see all that stuff on the sides of the flask? Okay, that's just crusts of sodium chloride that have deposited together. Okay, so it stopped floating around and it has deposited onto the glass. And that's it for that. Not a terribly long clip today, but it really does show the difference. And yes, you're absolutely right. You could eat that stuff once the nasty cloud is gone. I know, sounds insane, but there we are. All right. So the moral of the story is that compounds have very different properties to the elements from which they are made. Another example we could look at carbon Okay, and we can look at the element oxygen. What does oxygen do to a flame? Like if you put oxygen to a flame, yes? It makes it bigger. Oxygen is very flammable. It makes the flame bigger. However, if we take the carbon and we put it together with the oxygen, we end up with the compound carbon dioxide, and that's actually one of the components in a fire extinguisher, which puts the flame out. So once again, you can see the element oxygen is very different than the compound carbon dioxide. The properties are very different. We're going to do a bit of jumping about today. Okay, so we are now going to head over to page 114, 1.6c. Once again here, we are doing some spaced repetition. You learned about scientific notation already, yes? Now we're going to learn about it in a little bit of a different context. We're going to add on a little something so it's a reminder of what you already know, but it's an add-on to what you already know. So here we have a number in our first example, 29.4. And this number is not in scientific notation. And what I would like you to do is I would like you to chat with your partner and decide why that number is not in scientific notation. Why is that number not in scientific notation? Yeah, for sure. Okay, so what's wrong with it? What do we have in front of our decimal? We have 2 digits in front of the decimal. When you're in scientific notation, how many are you allowed? 1. So how many non-zero digits should be in front of the decimal in scientific notation? The answer is 1. So we're now going to take this number, which is in what I call no-no notation, because it's neither scientific notation nor standard notation, so it's a no-no. Don't write numbers like this, okay? And we're going to convert it into scientific notation. So we need to move our decimal so that there is only 1 non-zero digit in front of the decimal. So here is 29.4, and we move our decimal how many places? 1 place. Okay, so instead of 29.4, now we have 2.94. As we went from 29.4 to 2.94, what happened to that number, to the coefficient, right? Because we are looking right now at the, ooh, that was supposed to be a highlighter. We are looking right now at the coefficient. What happened to it? Did it get bigger or did it get smaller? This got smaller. By how many powers of 10 did it get smaller? 1 power of 10, and we know that because we moved the decimal place 1 place. So it got smaller by 1 power of 10. In order for these two things to stay equal, we're going to also have to change the power of 10, because if we leave it as a 10 to the 1, these two things will not be equal. So if 29.4 got smaller, what's going to happen to the power of 10? The power of 10 will have to get bigger, okay? So this got smaller. And so the power of 10 has to get bigger. If that makes intuitive sense to you, that's wonderful. If it does not make intuitive sense, I have an example that will hopefully help with that. At the bottom of the page, when you multiply two numbers, if you make one of them smaller, the other one must get bigger in order to stay equal. So this is right at the bottom of the page. We have here 3 times 4, okay? And 3 times 4 is equal to 12. Easy peasy, yes? What if I took that 3 and I turned it into a 2? Yes? So the 3 became smaller and became a 2. The number it's multiplied by, in order for it still to equal 12, the other number must get bigger. In this case, it would become 6 in order to still equal 12. So that's why in scientific notation, if the coefficient gets smaller, the power of 10 has to get bigger. If the coefficient gets bigger, the power of 10 has to get smaller. That way they stay equal to one another. So let's do this. The mantissa, or the coefficient, got smaller by 1 power of 10, because we moved the decimal place 1 position. And so the 10 to the 1 is going to have to get bigger by 1 power of 10. So what's the 10 power going to become? It's going to go from 10 to the 1 to 10 to the 2. Okay, so 10 to the 1 becomes 10 to the 2. So 29.4 got smaller by 1 power of 10. And the exponent got bigger by 1 power of 10. We can prove to ourselves that these two things are equal. We can say, well, if I took my 24.9 times 10 to the 1, 10 to the 1 is just 10. So 29.4 times 10 is 294. Yes? We take our other version of the number, the one it is in scientific notation, and 2.94, we have 10 to the 2, so that's 10 times 10, which is times 100. 2.94 times 100 is also 294. So we can prove to ourselves that in fact they are still equal once we've moved the decimal place and changed the power of 10. Okay. What is wrong with the number in example number 2? Talk with your partner. If you don't have a partner, you can turn around, talk to the person behind you. What's wrong with that number that makes it not in scientific notation? What's wrong with this number in front of the decimal? That can't be a 0 in scientific notation. The number in front of the decimal cannot be a 0 in scientific notation. That's my little abbreviation for scientific notation. Sci, and then NOT with a little N at the top, scientific notation. What should we have in front of the decimal? It should be the 4. We should have a single non-zero digit. So what will we move in order to get this into scientific notation? We are going to move the decimal so that there is what in front of the decimal? 1 non-zero digit. In front of the decimal. So here's our decimal. We're moving the decimal one place. That means it's changing by 1 power of 10. So we went from 0.4837 to 4.837. So that number got bigger or smaller? Hold on. It got bigger. Yes? So the coefficient got bigger. It went from 0.4 something to 4 something. Yes? So the mantissa or the coefficient got bigger. That means that the power of 10 has to get smaller. And the coefficient got bigger by how many powers of 10? Yes, 1 power of 10 because we moved the decimal place 1 position. Yes, of course. So that means that our power of 10 has to get smaller by 1 power of 10. Smaller than 10 to the 2 is 10 to the 1. Okay. So we take this number, which is in non-scientific notation, and we have now changed it into scientific notation. (348) times 10 to the negative 5. We're going to do the same thing now, but with negative exponents. Make sure you're good with those. 348 times 10 to the negative 5 is not in scientific notation. Why not? Yes. There is no decimal, but I could write a decimal. And in fact, if I wrote 6 times 10 to the negative 3, that's completely good scientific notation. Okay? So what is wrong with this? We have a bigger number. Specifically, what is in front of our decimal? How many digits in front of our decimal? 3. But we are only allowed to have 1. So to fix that, let's move the decimal so there's only 1 digit in front of that. That means we're going to take it from here and we're going to move it in between the 3 and the 4, which would change it from 348 into 3.48. Did that coefficient get bigger or did it get smaller? The coefficient got smaller. 3 is smaller than 300, yes? So it got smaller. Tell your partner, by how many powers of 10 did it get smaller? We moved our decimal 2 places, therefore it got smaller by 2 powers of 10. That means that our exponent is going to have to get bigger, because it always has to do the opposite. So it has to get bigger by the same number of powers of 10, so by 2 powers of 10. Now I'm going to ask you a question here. Which one is the bigger? Is it, we have 10 to the negative 3, we have 10 to the negative 5, and we have 10 to the negative 7. Will we turn 10 to the negative 5 into 10 to the negative 3 or 10 to the negative 7 in order to make it bigger? Yes. We're going to change it into 10 to the negative 3. Okay, that one's right. That one wouldn't be right. The larger the smaller the negative exponent, the bigger the number. So for example, if I was to have 10 to the negative 3, that would equal 1 over 1,000. 1/1000th. But if I had 10 to the negative 7, that would be 1 over 10 million. So that would be 1/10,000,000th, which is a heck of a lot smaller. Yes? Yeah, of course. So this has to be to the negative 3. Example number 4. 0.005279 times 10 to the negative 3. What is wrong with that makes it not scientific notation? Yes. There's a 0 in front of the decimal. Cannot have a 0 in front of the decimal. It must be a non-zero in front of the decimal. So we need to move that decimal how many places? 1, 2, 3 places. Did our coefficient get smaller or did it get bigger when we moved that decimal? It got bigger. And it got bigger by how many powers of 10? 3, because we moved our decimal place 3 places. That means that our exponent must get smaller. And it has to get smaller by 3 powers of 10. Tell your partner, what is 3 powers of 10 smaller than 10 to the negative 3? That would be 10 to the negative 6. Yes? Because the larger the negative exponent, the smaller the number. And now we have just 2 funny little ones. Yeah, sure. 2 funny little things. Here's one. Is this number, example number 5, in scientific notation? No, what's missing? We need a power on our 10. And I'm going to give you a couple of choices here. We have 2.3 times 10 to the 0 or 2.3 times 10 to the 1. Which of those is equal to our original number, 2.3 times 10? Are you sure? Well, let's think. Remember, what does 10 to the 0 equal? 1. Okay. What does 10 to the 1 equal? 10. So this number here would equal 2.3 times 1. Is that what we started with? No, because we have a 1 here, and up here we had a 10. Yes? 2.3 times 10 to the 1, though, because 10 to the 1 is 10, that's 2.3 times 10. Is that what we started with? Yes, it is. Okay, because we have a 10 there and we have a 10 there. So this one is wrong. This one is correct. Those can be a little tricky, so make sure you do think it through, you know, if you're not consistently getting them correct. 4.6. Is that number in scientific notation? No. What do we need? We need times 10 to the something. Okay, so again, I'm going to give you 2 choices, 4.6 times 10 to the 0 and 4.6 times 10 to the 1. Decide with your partner what you think. Is it 10 to the 0 or 10 to the 1? Remember, of course, 10 to the 0 is equal to 1. 10 to the 1 is equal to 10. So 4.6 times 10 to the 0 is equal to 4.6 times 1, which is equal to 4.6. Is that what we wanted? Yes, it is. That's what we started with. If we do the other one, 4.6, 10 to the 1 is equal to 10. That would give us 46, which is wrong. That's not what we wanted. This is what we wanted. Is good? Okay. Last thing for today, and then I'm going to give you some time to work on the homework. 1.7a is on page 118, although I'm going to go a little off script on this because in 1.7a I've shown you 3 different methods of solving the equation. Today, to streamline things, I'm only going to show you one method. If you like the other methods, or if you can do this in your head without writing anything down and just like be like, bam, I've rearranged the formula and there it is and I've got it correct, that's perfectly okay. Okay, so your method, if it's just in your head or some other way, is perfectly good. But I'm going to show you one that was really effective for my grade 9s. So I figure if it was really effective for them, it will also be really effective for any of you who have not had enough drill, perhaps, in how to do simple algebra. Because you don't anymore. You don't get enough drill. You're busy transforming graphs and moving things all over the place, and basic skills are being just like sort of left behind. Anywho, solving an equation. We're going to take, for example, A is equal to B over C. And we are going to solve for B. So, yes, yeah. Solving for B involves 3 things. You need to get B on the top, which means in the numerator. Yes. Yes. But that's okay. Like if you can do it in your head, you're good to go. Okay? Yeah. So we need to get B on the top. Like I said, if you can just already do this in your head, that's totally fine. Okay? I'm going to put a line there just to remind myself. Yes? Yes, for sure. And if you're like, I'm totally done with all of this and I'd just like to do the homework, you can go on Teams and look at what our homework is. Okay. We have A here, and it's on the top, and there's nothing in the denominator. Well, really, there's not nothing. There is a 1. We're not going to write it. We're just going to draw this line so we know that there is a place for things underneath A should we want to put them there. So B is already on the top. We need also to get B by itself. Okay, so B is going by itself. Is it by itself? No. Who's cluttering up the B? That would be C. C is messing up the B. B wants to be all on its own on one side. And this is where we get to the method that I like, and it's the diagonal method. And in the diagonal method, you can move variables across the equal sign, but they have to move diagonally. Okay? Variables can move to the other side of the equal sign. Only diagonally. So what I'm wanting to do is I'm wanting to get C out of the right-hand side and onto the left-hand side. There's two places it could go. It could go into the numerator, or it could go into the denominator. If I move it into the denominator, has it moved diagonally? No, it has moved straight across. So what I'm going to do is I'm going to move the C diagonally up. Okay, and now it is in the numerator. C A equals B. This would be the same as writing C times A is equal to B. The time sign is optional, okay? The third thing you'll need to do, and this is because in chemistry, normally we're not just solving for a variable. Normally what we'll do is we'll solve and then we'll plug in some numbers with units and then we will solve the entire thing. We also want B to be on the left. And the nice thing about this is, let's say I gave you 2 times 3 is equal to 6. Yes? What if I wanted the 6 to be on the left? 6 is equal to, what would I put on the right? 2 times 3. Anytime I have an equation, if I just want to take the whole thing and flip it, it stays equal. Okay? You can always flip everything left to right. So we can actually take the C and the A and the B, and we can put those on opposite sides. So then we will have B is equal to C times A. Is good? Okay. I will say that this next example is the one that is most likely to be done incorrectly. So even if you think you know what you're doing, what I'd like you to do is I would like you to try to solve it, and when I'm done solving it, I want you to check your answer and see if you got the same thing as I do, okay? So we are going to solve for C. So see if you can solve for C, and then you can see if you get the same answer as I do, because this is where people will, if you're going to go wrong, this is probably where you will go wrong. So we need C on the top. That's the first thing we have to do. Is C on the top? No, it's on the bottom, and I cannot move it straight across into the denominator. I have to move it diagonally up into the numerator. Okay, so it's going to move diagonally across the equal sign. So we have C times A is equal to B. The second thing we have to do is we want C to be by itself. Is it by itself? No, we have the letter A cluttering up the C, and I'm going to put my lines here so that I remember that there is a denominator there that I could move things into if I wanted to. So I need to get rid of the A, and I'm going to do that by moving it to the other side. I cannot move it straight across. I need to move it diagonally, which means it's going to go down, okay, into the denominator. So now we have C is equal to B over A. So 3, we want C on the left. And lo and behold, oh, it is on the left already. We're good, we're done. So check your answer and see if you got C equals B over A if you were doing it on your own. If so, give yourself a little pat on the back. Yay! Okay. And finally, one last example. We have A is equal to B times C, and we would like to solve for B. What is the first thing we need to do? We need B on the top. I'm going to draw in my lines so I can see that there is a bottom should I choose to use it. Is B on the top? Yes, it is. Hooray! We need B to be by itself. And it is not by itself right now. It is cluttered up by this C over here. So we're going to take the C and move it to the other side. When we move it to the other side, it must move diagonally. So it must move into the denominator to move diagonally. So now we have A over C is equal to B. And finally, we need B on the left. So we will take the whole thing and we will do what? Flip it. And we get B is equal to A over C. And we are done. Your homework, number 1, page 50. Number 2, page 116. Thank you. Number 3, pages, where is it? I think it's 122 to 123. Yep. 122 to 123. I know we have hardly time left at all, but pick one of them, see if you're doing okay on it. Make sure you're checking the answer key to see how well you're doing. And if you're not getting the correct answers, it would be a good idea to drop by tomorrow during flex if you don't get a chance to ask today, because we're almost out of time. We've only got about 7 minutes left. But see what you can do in 7 minutes, okay? Oh, and then the fourth thing, of course, is to work on your visual dictionary vocab list. That's sort of ongoing. Because remember, there will not be a quiz on that stuff. It will just show up on your test.